Okay, hey everybody, and welcome to this presentation with the title Java 24 is faster than ever. And now you think, you guys always says that the latest version is the fastest, don't we? But I think it carries some weight. We are putting in a lot of work at Oracle and at other organizations to keep your application running as smooth and as fast as possible. But the question is, why is it faster? And I think we are going to open the hood a bit and see why it can be faster. So my name is Per, that's my social handle, and I work in the core Java library team at Oracle. And here is the agenda. So we're going to look into a few of the JDK products we are working on currently because they all relate to performance in some way. Then we're going to look at some metrics. How do we measure performance? What are the challenges? What are the tools we have? And then I'm going to spend quite a bit of time to elaborate on the JIT-compiler tricks that we can play on your code so it can run faster. And that section will take about a quarter of an hour, so prepare for that. And then I have promised to do 5 recent performance improvements, which I think what you are here to listen to. But maybe we have time to look into a few more. Let's see how much time we have. And then I'm going to wrap up talking about the evolution of Java, what's ahead of us, and how you can test your application with the newest JDK. And then maybe we can have some questions and answers at the end. Okay, so here is the list of most of the products we are working on currently on the OpenJDK community. We have Amber, which focuses on smaller language features. I would say that some of them aren't really small. We have add records, we have pattern matching and things like that, which I think is quite a big feature set. And so far, we have delivered about 25 JEPs, and some of them will improve performance of your code. We have product Babylon, which has a very ambitious goal to reach other domains, such as SQL or machine learning and GPUs. And that relies on something called code reflection. Now, up until now, we could reflect on a field. We can see what's the name of the field, what's the type, and so on. But with Babylon, we can inspect the actual logic in the code. And maybe we can take that logic expressed in Java and then compile it to a core and load it into a graphics GPU or on a machine language kind of dedicated hardware. And that would be nice. We can all stay in our favorite language but still execute with great performance. We have Product Legion, where the intention is to improve the startup and warm-up time. Many of you deploy applications in the cloud, and maybe you spin up and take down your or lambdas or whatever you have out there, and then you're interested in getting up to speed as soon as possible. And we're going to talk about that later on. We have product Lilliput, where the objective is to shrink the headers. I think you're aware that when you create an object, for example with an int, there's a lot of other things going on there under the hood. It needs to have maybe a hash code. It needs to keep track whether or not there is a lock on it and stuff like that, which class it is. And all those things are put in something called the object headers. And there's an effort to shrink this header so we can save memory. And that's not all about memory, because if you shrink memory, then we get better locality in our code, and it will run faster. Product Loom has delivered a large kind of deliverable recently with the virtual threads. But there are still some things we are seeing improvement there, and we'll talk about that also later in the presentation. Product Panama is something that I've personally been engaged with. That is calling native function and memory API and also vector support. And we have actually we have succeeded in improving performance for many of the bulk operations there. We have product Valhalla that's been going on for over 10 years. And now it's only 1 year left or something like that before we can see the benefits of that. But that will also improve performance potentially significantly when we can have flattening of objects, for example, in arrays, eventually. So the battle cry there is codes like a class, but works like an int. So we can kind of heal this rift between primitive types and the wrapper types, and we can even create our own primitive types, so to speak. Maybe we would like to create something like a complex or something like that, or a float 16. We are also working relentlessly with GCs. So there is a new GC called ZGC, which I'm sure you have heard about. And there has been recently some improvements in that as well. So let's continue. You might think that this is very, glorious to work with performance. You sit there and watch machine code, and you're doing experiment and twiddling bits and so on. But most of the work is actually, preparing for upcoming features, fixed regression that we caught internally, or maybe some user got back and said that, well, this is not great. Can you do something about it? And also, implement features that we have used, but then use them internally in the JDK. For example, we released the project PAM and the FFM lib in JDK 22, and now there is a work to kind of use that internally in the JDK to benefit from the benefits there. And that always introduces some challenges in terms of performance, but also open up for some opportunities. Okay, so let's talk about the metrics. What do we mean with performance? So we have metrics in the temporal domain. The temporal domain is about time. So one very common metric is the average throughput. That is the number of operations I can do per second, or the number of megabytes I can chew through with my algorithm. But there are others that are, could be said equally valid. So there's something called typical latency. So suppose I do 1 million of experiments, and then I order them all in order, and then I look at the middle, and that is the typical latency. And that might be quite different from the average throughput, actually, depending on distribution. And there is something called the worst case scenario. So maybe I do all this million tests, and then I only look at the 1%, top 1%, or top 0.01%, because it's important for me that we don't get this kind of outliers or exotic outliers. And it turns out that usually if you want a good worst case, you often have to sacrifice your average throughput to ensure that you get this kind of predictability. So there is a tension between worst case and average and all that stuff. And maybe you have, a certain shape. If you do this, then that happens, then you should have this requirement. So there are all sorts of temporal domain requirements that are out there. And then there are kind of indirect temporal requirements, such as startup time. Now, what is the startup time? The startup time is the time it takes from you start your application until it provides some useful work. For example, if you start your Hello World, it's time from you start it until it prints on the screen. Or maybe more realistically, if you deploy a web application, it's the time it takes before you can serve the first incoming request. And that is something that's measured maybe milliseconds or seconds or so. And then there is the warm-up time. And what is the warm-up time? What's the difference? So the warm-up time is the time it takes until you get peak performance or almost peak performance. As you will see later in the presentation, the code will go through different tiers of compilation. And so it takes a while for your code to really operate in the fastest way. And that is something we are working with as well. So that can be measured maybe in seconds or maybe in the number of invocations on your method that you are writing at the moment. Okay, then have we resource metrics, memory usage. Maybe you're doing a sort algorithm and might be faster, but might use more memory, and that's the trade-off. That's the kind of a performance metrics. My sort algorithm does only require half the memory as yours, and therefore mine is better, or something like that. We have memory access and patterns. It turns out then the way you access memory can also affect your algorithm, but it can also affect other methods that are out there. We have something called memory pressure, which is the number of objects you allocate, and then there has to be freed. So that's usually referred to as memory pressure. And there is thread usage. Maybe I use a parallel algorithm. Well, it's faster, but it consumes a lot of threads. So that's another resource metric we should be careful with. Maybe we use the CPUs in a certain way. That's not good. We have cache locality. So if my code is using things that are very local, things are being scoped up from the local cache, like the level 0 cache, the L1 cache, or L0 cache. Whereas there's a great difference if I have to go out to main memory and collect the things I need. We have contention around resources, like a monitor or something like that, and that can affect performance. And of course, code size is another trade-off. Maybe I have an algorithm that's much quicker than another one, but my code is much bigger, so it consumes more of the available compiled code, the code cache, it's called in Java. Maybe I use SIMD operations like vector operations, And they are also a scarce resource. In some hardware application, the number of SIMD registers is limited and so on. Okay. And there is also a consideration. So if you look at the platform, wow, this is not in sync. Okay. So maybe if I have a platform, there is a certain CPU type. So my algorithm might run good at x64, but not on ARM for some reason. And some of the different generations have different compute to retrieve ratio. If you look back when I started with Java in the 90s, the compute to retrieve ratio was almost 1. I want to add something or I want to get it from memory, it was about the same time. But these days, not so much. It's like 100 cycles or even more to just get in 64 bits of memory, whereas it's just a few cycles to compute something. So there's a huge difference in that. And then we have number of cores. Maybe my application runs great in single core, but not so great with several. What kind of GC I'm using might affect a little bit. And how many threads I'm using is another thing. So all these things add up. And there's, of course, also workload distribution. How is my application used? What's the shape of the data? What's the actual content of the data I'm using? For example, in a sort algorithm, is it always sorted or almost sorted, or is this just random? And they will behave completely different for different algorithms. And there is something called pollution, which is a bit ahead. I was going to explain that more in a few slides. But pollution is when the code compiles to machine code, the JIT-compiler makes some assumptions. But if those assumptions are broken later on, performance is not great. And that is usually referred to as pollution. OK. But what we usually focus on here is the average throughput. That is the number of operations per second. That is the usual optimization criteria. And we measure that after warm-up. And therefore, we're talking about compiled C2 performance. I mean, we have to be clear here that there are different compilers in Java. There's the first Java C compiler that takes your text file and converts it into bytecode. That's one compiler. But I'm talking about the compiler that takes the bytecode and converts it into machine code. And that is the JIT-compiler, and that is called the C2 compiler. So the reason is, if it ain't compiled, it's hardly used anyway. So if you don't use it, it's not worth spending so much time and making it faster. It doesn't matter anyway. And we also have to look at all the supported platforms. So we have, of course, Linux, and Linux is x64 and A64. We have Mac, A64, and not so much x64 anymore because it's kind of disappearing. And then we have Windows on x64. Those are the main platforms that we are evaluating performance on. So we have this kind, and I apologize for the colors here. It's been recycled. But we have this kind of positively feedback loop here. So if something is used much, it's getting faster, and therefore we tend to use it more. And then we also focus more on improving the performance of such methods. OK, so what are the challenges and solutions when we do performance? So the first one is don't use a laptop. That's a classical mistake because the performance of your measurement will depend on whether or not you have your power inserted. If I take out the power, usually the computer will be more conservative with using power. Maybe I have increased the luminance of my screen, and that consumes energy, and therefore my computer might run slower, or for any other reasons that you don't really are aware about. Run the method sufficiently before you measure performance. You must have a warm-up period. So it's about 30,000 times before you have collected enough of profile data before it compiles. And then it also takes some time to compile. So you have to give it a second or so, give or take, before you actually measure something. And it's been more than one time that people come to me and say, well, I've tested the performance of the method you wrote, and it's really slow. Look here. And then they run it once. OK. So that doesn't say anything. You should use this system nanotime because that is a monotonic timer. It always increases as time goes by. But there are other timers like system milliseconds that can be adjusted depending on if you're connected to a network, for example, it adjusts the time. So actually, your test can run in negative time if you use that. And of course, that's encouraging, but not connected so much to reality. And the JVM is pretty good at inferring constants and fold and speculate about stuff. So that is something you have to look out for. Maybe you are testing something that's actually not tested. So we have a great tool called JMH, the Java Microbench Harness, that fixes most of the things for us. So you write a benchmark, you annotate it with benchmark, and that properly consumes whatever you're returning from your method. So it will not eliminate that code, because if you don't consume it, the VM might see that it's not used for anything, and therefore it's not even required to do the actual computation. And then, of course, your method will be super fast. But it didn't say anything about solving the actual problem. It also prevents inlining of input data. So if you call your method with all the same parameters, then of course the VM will realize that, and maybe it will take some shortcuts. And then if you provide real data that will vary, the result will be totally different. And that's not something you would like to discover in production. And it runs several rounds in separate VMs, so therefore you can kind of see what are the variants in the different tests. It adds a warm-up phase, and because it runs several times, it's possible to estimate the error margins. What's the confidence that this actually is a true value? And here is an example that I wrote a while ago. So this is benchmarking a fill method that has a memory segment, fills it with a byte, using two different benchmarks. And as you can see, they mark with benchmark, and then I set some kind of JVM parameter there, and then one of them runs, and then the other runs. And as you can see also the element size, it will run these tests with a different of sizes. So I have a bunch of small sizes, and then I increase the sizes to see what happens. And
what was the fork value about?
The fork value is how many JVMs it will do before it kind of concludes. Now I have this discrepancy between the screen again. But here's how I run it. And it takes minutes, of course, because it has to do all these forks. It has to run all these variants. And then I end up with the first one there, executed in 0.7 nanoseconds. And the one at above was much, much slower. And this actually revealed something I will talk about later. So you can see there's a big difference between 0.7 nanoseconds and 53 nanoseconds. Something is obviously wrong below there. Okay, and you can also export the results here and import them in various tools. So you can see bars, and you see the line there indicates the error of margin. So you can get a feeling of that. So if the error margin is much bigger than the actual difference, then you might not be able to say something about your actual test. So here is the output. I have taken the output from the benchmark and I put it in a chart, and then illustrated base, which is typically what you have, and then patch is your proposal. And my proposal here was to use this patch with the red. That's obviously much quicker for lower values in this field test. And this was ran on a Linux x64 platform. And I think that gives you a good way of seeing what's the pros and cons of different algorithms. And of course, we run in Oracle, we have a huge farm of computers where we can do before and after tests on different platforms. And typically you can see something like this. It doesn't look like this for real, but this is just an illustration. So maybe I didn't change foo and bar, but I updated bas. And my change was green there, showing that in all these platforms, the performance was improved. But maybe I did something not so good in Quix, because performance was worse there. And we ran these tests all the time for all of these to kind of capture any regressions. Okay, so that's that. Now the next section is about compiler tricks. And this is a bit technical. So before I start here, I would like to speak about the circle of life for Java code. So when we start our Java application, it starts in tier 0, which is interpreted mode. It will look at every byte code, execute it, and then sometimes insert save points, and then look at each byte code. And of course, that is slow. It takes a lot of time to do that, and that is why it's not warmed up. And when it does that, it will profile your program. It will, insert statistics. How often is this branch taken? What kind of parameters are received here, and so on. And then it will advance and be more and more specifically compiled until it comes to something called tier 4, which is the C2 or Graal compiler, which compiles to machine code. And then it's using all this profile data and trying to emit as efficient machine code as possible so that your code can run as fast as possible. And then if this profile changes, or if a speculation, because I didn't mention it, but the compiler is able to speculate about your input code. So it can say that, oh, this method was called 30,000 times, and at no time there was a null provided. So I can speculate that the parameter here will never be null. And so it inserts a trap, and then it can optimize all the code, knowing that this will never be null if this kind of trap doesn't trigger. And then your code will run super fast. But if you then provide null, the trap will trigger, and we will go to de-optimize and go back again and recompile. So that is a cool feature of the JVM and the JIT compiler. Okay, so I'm going to present kind of a Rosetta Stone for compiler wannabes, nerd wannabes. I'm going to talk about inlining, loop unrolling, hoisting, dead code elimination, auto-vectorization and superword, which are related, pre- and post-alignment, and long-to-int looping conversion. How many of you have heard of anything like this? Okay, so we have some experts here, but not so many. So that's great. Then you're in the right room. And also we're going to talk about some concerns, which are aliasing and control flow. Don't worry so much if you don't understand this now, because I will go through them each and every. So let's take a very simple example, somewhat inspired by reality. So I have a method here that takes a source and a destination array, and then I copy everything from the source to the destination, and I'm copying byte by byte. Nothing special there. And then I declare a source and a destination array, and then I invoke my method, copy source destination. So hopefully this will copy whatever is in the source, and it will end up in the destination below there. Nothing advanced. But the compiler can inline this, and it can say that, well, I can remove this function and do them in succession instead. So this code is equivalent. So I create my arrays, but then I don't have a function. I just flatten out the code and put it after the creation of the arrays. So this is a transformation that will yield exactly the same result, but I don't have to put the parameters on the stack, and I don't have to invoke another method. It just runs from start to beginning. So that would be a little bit faster. But that's not the big upside. The big upside is now that the compiler is able to see more code at the same time, so it can do more optimizations.
So it also inlines the system copy thing. So doing this for.
We will see what you can do about that. So let's see here. So this is, up until now, this is just a model I'm illustrating. It's not changing the Java code. So it's just an internal model of the different nodes that's in your code. And then we can do something called unrolling. And the unrolling is that we can amortize the cost of iterating every time by doing several operations at each operation. So here I've elected to show the case when we have unrolled from 1 to 4 copies. So you can see that on the right-hand side, that I increase my I by 4 instead of increasing it by 1. And then I do 4 operations. So that means that I have reduced the overhead by 24%, 25% almost for iterating. And that's called unrolling. Now we come to the next thing called hoisting. And here I've done a little trick. I've made a transformation that says that instead of checking the array bounds for every read and write, I'm doing the bound check once and for all outside the loop. So I'm checking now here that the length of the source is not longer than the length of the destination before I enter the loop. And then throw an array out of bounds exception. And then I've changed the brackets to parentheses there, indicating that this is an unchecked operation. So I don't have to check the index there. Now you might argue that this is not a really correct transformation, because if there is an exception, in the previous example I would do a partial copy, and here I won't do a partial copy. So they are not exactly the same, but I hope you understand the analogy here. Okay, so that means that we don't have to do bounce checking for all of these operations, and they can basically be just machine code copy operations.
Since when is that?
That's been along for a long time. And actually, if you look at this a little bit more, if you squint a bit, you can see that we can determine that the destination array is always the same length as the source length here. So I don't even have to do this hoisted check. I can just remove it. And that is dead code elimination. And then, maybe I don't want to work in units of bytes, but I can do something called auto-vectorization, which is that instead of looking at these elements as byte, I can look at the elements as longs. So I can use copy 8 of them instead of just 1 for each operation. And of course, there is an overhead for each operation, so that will make my code faster. So then I kind of get something as long array. So I look at my address basically for the array, and then I say, no, now it's suddenly a long array instead. And then I operate on steps with 8, and the ... at the end indicates that there has to be some kind of mop-up operation, because what if my length is not evenly divisible by 8, then I must take care of the remaining ones there. But it's not the end. So I can, instead of using a long, long is the longest unit of data that is there in Java, but under the hood there are SIMD operations that can be, for example, 512 bytes. That is 64 bytes instead of just 8 bytes. So I can do that instead and work with an even larger chunk of data, and that will improve my performance even more. And if you don't use the vector API, you don't have access to these kind of operations in Java. But then, it's not the end there. I can combine hoisting and unrolling again. So I can say that I only want to convert the address of this once. And then I do several of these vector operations. And then I do my loop. And then I can work with kind of units of 256 bytes at a time. And that is a big difference in terms of performance. Now, in reality, an array can actually move. The physical address of an array can move because the garbage collector can move stuffs on the heap. So before I do tricks like this, I need to pin them and saying that if the garbage collector wants to move them, they're not allowed to do that until we exit and unpin this. So there are some caveats with doing things like that. And of course, we have the mop operation down there. And then we have pre and post alignment. This shows an example where we have kind of 64-bit units evenly in memory. And what if I start with A, B, which is not properly aligned? Then on some platforms, it pays off to do kind of a header before I get to this alignment here. And then I do like bigger operations, and then I do a mop-up at the end. So that's pre and post alignment. I think this is more relates to older hardware. It's not that super important on new hardware.
Once you do all that, can't you run parallelly to get more?
Yeah, you can do that as well. Yeah, but that's another story. So here is an example of post and pre alignment. I think I will skip that. Okay, and there is something called long to int looping conversion. So if I have not an array, but something called a memory segment, which models 64-bit memory segments, and then I have a long to iterate. It's more expensive to use a long than an int, so I can break it up using 2 int operations. I have an inner, which is usually doing the hot loop, and then an outer loop. So that's another trick that we can do. So coming to the problems, there is something called aliasing. So if we look at, we have a memory segment with some contents, A, B, C, D, and E, and then we want to copy it to something that overlaps. That creates a problem because I do it byte by byte. I copy the A to the first position of the destination, and that is the same position as the B. So now B will contain an A. And then I can take the next one, which is now is an A, copy it to the next, which replaces the C, which now also is an A. And then take the C, and the A and copy to next, and so I will only end up in A at the bottom because they overlap. But if I work with larger units and take, say, for example, 4 units, I will take ABCD and copy ABCD into the one below. Obviously, the result will be different. So you have to be very careful if you have aliasing. And if you have 2 heap arrays and they are different, then you know it's not a problem. But if you have a native address, it's more tricky. But it can be done. Control flow is another thing. So control flow means we are jumping or we're returning for some reason. And as you can tell here, that we have a mismatch method that says where is the mismatch between those arrays. And if I jump there, I might have a problem because if I have larger units, I don't know in which position in these units was the difference. Okay, that's that. So now let's talk about 5 or maybe more recent performance improvement. And just yesterday, Claes and I released this article on Inside Java, where you can go and read more about performance improvements in Java 24. So here are some of them. So there's something called MergeStore. So some of clients write code like this. So here I have an array of bytes. I have an offset, and then I have a long. And the idea is that I want to insert my long into this array somewhere. And I do that by shifting my value and then having different offsets here. And this looks quite slow because I have to take V, shift it, then take that byte value, put it in the first, then shift it by 8, and so on. But the cool thing now is that the compiler is able to see the pattern here. And it can just take the long and just write it into memory. So that means that the performance of this operation will increase by several times. And that's called MergeStore. And you don't have to change your code. You get this for free if you have something like this. But it doesn't always work if you are updating your offset as you go along. The JIT-complier is not able to do that. So if you want to do something like that, it's better that you update it at the bottom here. And then you still will get the performance of this feature. So FFM API bulk operation, I've been talking about them before. I told you, you have something called memory segment, which models a 64-bit continuous region of memory. And it can both be on heap and off heap. And there are then some bulk operations on those segments. For example, fill, which fills your segment with a specific byte value. There's a copy that copies from one memory segment to another. We have a mismatch, which detects the difference between 2, if there is any. And then string length, which determines the string length of a C string. That is looking for the null value. And they were internally backed by unsafe, which is mostly intrinsic and native code. And there was also the allocate method. Every time I allocate memory, it needs to be zeroed out, and therefore fill is called. So allocate was also affected by this operation. And we were surprised to see that Java was actually faster than native machine code, especially for smaller values for memory segment. And the reason is that it's a price to transition from Java to native code that you have to pay. So for smaller values, it's actually faster to do this in Java. And that's what we did. So you can tell, as you can tell, the red one shows better performance. And that was the patch we put in. And we made a mistake. So in R64, the native method were very slow. And therefore, the difference here was much greater when we transitioned to Java. So that will be a huge difference if you run on ARM, if you use 64-bit ARM 64 architecture. And here you can set the threshold where it will go from Java to the native ones. And for the bigger kind of sizes, it pays off to do it natively. But for smaller sizes, and even for all sizes on some platform, it will be faster. So you can set this by yourself. And here is how the fill operation is actually done. If it's lower than the threshold, we do this in Java. But if it's higher than the threshold, we invoke this set memory operation, which delegates to native code. Yeah, that's that. OK, and the fill operation was equally improved. The red one is Java, and the blue one is native code. Copy, the same, faster for smaller values. Here I have mismatch, and here we have turn it around, so larger values are better. So the red one is larger and therefore have better throughput. Okay, and there is more to come. So we are working with this continuously to make memory segments faster and faster. We have improved auto-vectorization. We have C2 Graal improvements in the pipeline. Maybe we will increase those thresholds we have. And then eventually we will have the vector API coming, and that will give us a quite big boost in terms of performance. Okay, next one is the secondary super caching scaling. That was implemented for C2, and the purpose of that is to increase the speed for instance of expressions. So suppose we have a type called foo, which inherits from bar, which inherits from bus. And then I can ask, oh, I have a foo bar, is that an instance of bar? I mean a foo, is that an instance of bar? Yes, it is, and then it will cache that value. So next time I'll ask, is that an instance of bar? It will know that immediately. But if I ask, is this an instance of bus? Then it will not know, because it only knows that it's bar. So it will determine, yes, it is an instance of bus, and then it will cache that value and throw away the old value. And that's not so good. Imagine if you have multi-threaded application and you have running on different NUMA regions, there will be memory communication across this, and that's not so good. So what we did was we replaced it with an immutable lookup table, which is slower if you hit just one, but much better in the general case. And it was actually implemented in JDK 23, but in 24 we implemented it also for those more rare platforms. And the C1 still uses the old solution. Okay, string concatenation is another one. Here is an example for two different examples, but they have the same shape. So they take a string, an int, and a string. But it's about completely different things. But now the JDK is able to reuse kind of that template that we're using there. And it can also create the template much faster than before. So we used to use something called method handles, which you have method handles, you create a new method handle, create a new method handle, and every time you do that, you create a lot of garbage. But now, instead, we generate the class directly. So it's more efficient, the process. And that generated class has access to the internals of the JDK. And as I said, we can reuse those classes. So this gave us a 40% reduction in startup, a 50% reduction in actual code generated. So there was a benefit in startup and code generated, but the throughput, once we did all that, stayed the same. So the objective here was not to increase performance, but increase and improve startup and code generation. Another one is ZGC generational mode by default. So the ZGC is perfect if you have very big heaps in the terabytes. And it has much shorter stop the world events, so your application will not be so jittery. And it was introduced in JDK 15, and the kind of generational aspect was introduced in 21, but was off by default. So we turned that on by default in 24. So we think now much more application will actually run with the generational ZGC version. And we are looking at removing the non-generational ZGC quite soon. And this is how it works. So the big circle here represents the heap, and the different shapes there are objects. And if I create a new object here, let's say the star, and suddenly that goes out of scope because it was just a short-lived object. But if I want to discover that, I have to inspect all the objects. Now the idea is instead to have two regions here. So I have one for the kind of new and younger generation and one for the older generation then. And then when I create my short-lived object, it ends up here, and now it's easier to just discover it and throw it away. Okay, compact object headers was something I told about just recently. So the objective there is to reduce the object headers from maybe 128 to 64-bit, or more typically 96 to 64 bits. And so this will give us more compact heap and better usage. It turns out 20% of the memory is just object headers, because typically an object is quite small. So for example, if you have 96 to 64 bits, you will have 10% less memory. Yeah, and that will give you also a little bit performance boost because you have smaller memory, more locality. Okay, I have maybe some time left. A few minutes, so let's talk about synchronized virtual thread without pinning. I gave that a star because virtual threads are something very important we introduced recently, but unfortunately they were pinned. That means they couldn't be released from the carrier thread if they enter synchronization blocks. And that created a kind of a pain point. But that's been fixed now, so now virtual threads are just as good as any thread and can be scaled to use millions of threads. And I think we have 4 minutes left, so I think I just skip the rest and open up for questions. But before I do that, I want to point you to this URL here and where you can download JDK24 and try out yourself how much faster your code will run on JDK24.